It's time to change gears again. In this chapter, we return to the solar system and the processes that shape it. This is the theme that we will pursue until the end of the course. So to start with, we need to get an overview of our solar system and see how it compares with some of the other solar systems that have been discovered in the last couple of decades. We'll start this chapter with a tour of the main objects that make up our solar system. This will include the Sun, the planets, and the small bodies that orbit the Sun and the planets. Then we'll look at our solar system in a different way. Instead of focusing on the individual objects, we'll look at the big trends. This will give us a broad brush view of what our solar system is like. Finally, we'll look at other solar systems. In the past couple of decades, our technology has allowed us to detect planets orbiting other stars, so we can start to see what other options are possible as ways to lay out a solar system. We'll start our tour of the solar system with the Sun. As we mentioned at the start of the course, the Sun is an ordinary star, neither unusually large nor small. This means that it's a hot ball of mostly hydrogen and helium, with about 2% other chemical elements. Like most stars, the Sun's energy is generated by nuclear fusion in its core. Hydrogen is constantly being converted to helium, the same process that powers hydrogen bombs. The Sun is by far the largest object in the solar system. 99.8% of the mass of the solar system is the Sun. In other words, you could say that the solar system is just the Sun, and you'd be 99.8% right. How often are you that right? Since it's a star, though, it really makes the most sense to talk about the Sun in the context of stars, so we cover the Sun in much more detail in our stellar astronomy class. However, the Sun is still the dominant source of light in the solar system, and this plays a huge role in planetary atmospheres, so we'll be looking at the Sun's effects when we cover atmospheres later in the course. The 8 planets in our solar system are the 8 largest objects orbiting the Sun. Along with some of the moons, these planets will be the main focus of the remainder of the course, though we will also slip in some discussion of smaller bodies as well as planets around other stars. So to start with, you should make sure you know the overall geography of the solar system, where each of the planets is. Starting from the Sun, they are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. There are a lot of mnemonics, that is, memory tricks, to help people remember this list. One very common one is, "My very eager mother just served us nachos." However, you're welcome to come up with your own if you'd prefer. In addition to knowing where the planets are, it's good to start getting used to grouping the planets by size. It turns out that size is at least as important as distance from the Sun in determining what a planet is going to be like. So you want to be able to put the planets into their major size categories. The biggest planets are the big Jovians, Jupiter and Saturn. Next we have the small Jovians, Uranus and Neptune. As we'll see later, there are a lot of differences between these worlds and the big Jovians. Finally, we have the smallest planets, the terrestrials. They start with the Earth, then Venus, Mars, and finally Mercury, smallest of all. A little later in the presentation, we'll define these terms Jovian and terrestrial. But for now, we can think of them as size categories, with Jovians much bigger than terrestrials. Now we'll look more closely at each of the planets, starting with the ones closest to the Sun. As I just mentioned, Mercury is the smallest of the planets. As the world closest to the Sun, its surface is very hot. However, it's also covered in impact craters, the scars of collisions with asteroids and comets. This tells us that its interior is not hot enough to power geologic activity, a topic we'll look at in much more detail in a couple of chapters. Mercury also has virtually no atmosphere. Venus is almost as big as the Earth. It has a thick carbon dioxide atmosphere, almost 100 times as thick as the Earth's. This gives Venus a surface that's hotter than Mercury's. It also shows signs of lots of geologic activity, especially volcanism. And it's covered in sulfuric acid clouds. This makes the planet a lot like a classical image of hell. In contrast, the Earth's surface has a much more moderate temperature, and its atmosphere is much thinner than Venus's. The Earth's surface is also geologically active, but unlike Venus, Earth also has liquid water on its surface. The Earth has a unique atmosphere made of nitrogen and oxygen, and of course, Earth is the only place we know of with life. Mars is the last of the small inner planets. It's only a tenth of the mass of the Earth, and its carbon dioxide atmosphere is over 100 times thinner than Earth's. The surface of Mars is currently dry and cold, and liquid water couldn't last on its surface. However, Mars has had a much more interesting past. There are huge extinct volcanoes, a giant crack cutting across one side of the planet, and signs of ancient rivers that once flowed along the surface. Because of this, we've sent more robotic spacecraft to Mars than to any other planet, including several that have landed on the surface. The planets in our solar system are divided into two major categories, terrestrial and Jovian. The planets we've just looked at, Mercury, Venus, Earth, and Mars, are terrestrials. The word terrestrial means Earth-like, and that's what these planets are. They're small. In our solar system, that means the size of the Earth or smaller. They're close to the Sun, all less than 2 AU away from it. Terrestrials have solid surfaces, the sort of thing you could walk on. They have high densities, typically 4 or 5 grams per cubic centimeter. This comes from their composition. They're made of rock and metal. I've highlighted this point because this is the real defining characteristic of a terrestrial planet. If we found a much larger planet farther from its star, but made out of rock and metal, we'd talk about it being a big terrestrial in an odd location, but we'd still call it terrestrial. Terrestrials have few or no moons. Jupiter is the largest planet in the solar system. It's more than 300 times the mass of the Earth, and it's a very different kind of world from the ones in the inner solar system. Jupiter is mostly made of hydrogen and helium. On Earth, these are gases, but inside Jupiter, the high pressure turns hydrogen to a liquid, so you should think of Jupiter as a giant liquid world. There's no solid surface here, just thicker and thicker hydrogen the deeper you go, until somewhere near the center where there's a core of denser material. When we look at Jupiter or any of the other giant planets, what we see are clouds of ammonia and other hydrogen compounds. Saturn is a lot like Jupiter, even though it's less than 1/3 as massive. It's made of the same materials as Jupiter, though at slightly lower pressures. However, the thing you notice most about Saturn is its rings. The rings are made of billions of small pieces of ice orbiting around the planet like moons. We'll look at these rings more a little later in the section. Uranus and Neptune are the closest thing to twins among the planets. They're both between 14 and 18 Earth masses, and while they also have liquid hydrogen, a lot more of their interiors are made of rock and hydrogen compounds like water, ammonia, and methane. The outer planets, Jupiter, Saturn, Uranus, and Neptune, are called Jovian. Jovian means Jupiter-like, and we're looking at Jupiter here. These are very different kinds of worlds from terrestrials in many ways. By the way, no matter what your spell checker may tell you, the name is Jovian, not jovial. Jovian planets are big. The smallest ones in our solar system are almost 15 times the Earth's mass, and they go up to over 300 Earth masses. Jovians are liquid worlds. We sometimes call them gas giants, but this isn't a very good name for them. The high pressure inside means that even hydrogen is a liquid inside them, not a gas. This also means that there's no solid surface to walk on here. You can't land on a Jovian planet. The Jovians are far from the Sun, starting at 5 AU and going out from there. They have very low densities, typically less than 2 grams per cubic centimeter, and in one case, less than 1 gram per cubic centimeter. Once again, the low density comes from the composition. These are worlds with a substantial amount of hydrogen and helium as well as some of those hydrogen compounds, water, ammonia, and methane. This is the real defining characteristic of a Jovian planet, lots of hydrogen and helium. Finally, Jovians have many moons and rings. We'll be talking about the two types of planet all semester long, so it's important that you know the differences between them.